Welcome, everybody. It's my pleasure today to introduce Hannah Alpert, who will be telling us about homology of sliding squares configuration spaces.
Thank you. Guess I'll put up my slides. Okay. Okay. Thank you. Thank you for the invitation to speak. Thank you all for coming today. So I do have a theorem in mind about estimating Betti numbers of configuration spaces of sliding squares. That result is joint. Wow, let me see if I can just write that again and see why my tablet is not happy with me. That result is joint with Matt Kahle and Bob MacPherson. But mostly I'll just talk about starting to get some intuition for homology and cohomology of these configuration spaces and how we even start to think about them. So here's a picture of the kind of thing that we mean. We have some squares, they're all the same size, they're labeled 1 through n, and they're not allowed to overlap, and they're sliding around in a rectangle. And the configuration space has pictures like this as elements. So the configuration space I'm going to denote by C for configurations of n pieces in a P by Q rectangle, and that's the ways to arrange n labeled disjoint upright, so they're not allowed to turn, they're only allowed to slide, 1 by 1 squares, in a P by Q rectangle. So in this case, we have n is 3, p is, well, sometimes we go back and forth between p is the height first and the q is the width second, or the other way around. But I think in the paper, the first coordinate is the horizontal dimension. So I'll say 3, q is 2. And one thing that we are always doing in this setup is comparing to the situation where instead of a rectangle, we have the whole plane, so that the squares have plenty of space to move around. And our configuration space where the squares are confined to a rectangle is a subspace of that space. So this space where they have the whole plane, I'm going to denote by C of n. We can think of it as P and Q are both infinity. That's homotopy equivalent to if we just take the rectangle to be big enough, which in this case is going to be n by n. If there are n pieces moving around, as long as you have enough space in each direction that they can't sort of span that whole length touching each other, that's the same as having even more space. And this space is also homotopy equivalent to the space of configurations just of points, distinct labeled points in the plane. And that's a well understood, well studied space. It's the classifying space for the pure braid group. It's homology and cohomology are very nice and well described. So we're always comparing our configuration space to those spaces to those, and a lot of the geometry is the same, but since the squares have less space to move around, some funny things can happen where they have trouble getting around each other. So for interpretations of this, sort of why is this applied at all, we can be thinking of two main interpretations. One of them is that the squares are robot cars. You could be imagining a motion planning problem where you have some robot cars and they're all moving around on some kind of factory floor, and they have to coordinate somehow so that they can get to where they're going without crashing into each other. And problems like this do have topological obstructions. So it does make sense to ask about the topology of the configuration space in such a situation. The other interpretation that we often have in mind is that the squares are molecules. In this case, we would be imagining a really large number for n, lots and lots of squares, and we're thinking of them as very small, but equivalently the rectangle is very big. And in this case, one parameter that we would be thinking of is the density. So what proportion of the area of the whole rectangle do the squares take up? If the squares take up a large proportion, then it's like we have a solid substance where the squares can rattle around in place, but can't move very far very easily. Whereas if you have a low density, it's almost as if they're all moving independently and we have, say, a gas. So for this interpretation where the squares are molecules, we're always thinking of taking the limit as maybe the density stays the same, but the number of molecules is going to infinity, to model the situation where we do have a gas in a large container, or some substance with many molecules in a large container. So I've generally studied homology of these configuration spaces. And so to talk about homology, I want to start by what do I visualize geometrically when we talk about homology of one of these configuration spaces. It's a little bit hard at first to think about a configuration space having a shape. So I want to focus on this first picture. It's an example of how you would construct a homology class. So in this picture, what's happening, well, I made the squares look a little bit smaller than they really should be, just so that I could have room to show the boxes. But what happens is that we have two squares and they can go around each other in a larger square of size 2. So that's a circle's worth of configurations. And then simultaneously, while they're going around in a box of size 2, a third square can go around that box and make a second, like 1 parameter family of configurations. So then if we do those independently, we get a 2-dimensional torus worth of configurations. And then you keep iterating that. And in this picture, what we have, how many parameters? 1, 2, 3, 4, we get a 4-dimensional torus in the configuration space. So an injection from well, here I wrote J-dimensional torus into the configuration space. And from that, we can get a homology class. One way to think of it is to think of triangulating the torus to get, and then under the map, you get a singular cycle. Or you could think about it as saying the torus is a closed oriented manifold. So it has a fundamental class in homology. And then you can push forward that fundamental class to get a J-dimensional class, a class in degree J of homology of the configuration space. So that would be F star of the fundamental class is in the Jth homology. These other pictures are other variations of the same kind of idea. In this second picture, we really have the same thing going on, but we add a bunch of extra boxes. And the extra boxes don't interfere with our having a 4-dimensional torus. We can have these 3 squares going around to make a 1-parameter family in the first 2x2 box, and then 3 more instead of just 1 more in the 3x3 box, and so on. And then another thing that we can do in this third picture is, instead of just adding 1 box at a time, we can combine several of these boxes and have the boxes go around each other. So we have a 2-dimensional torus worth in each of these 3 boxes, and then moving the 3 boxes around gives us 1 more parameter. So in this case, we get a 7-dimensional torus. That can give us some homology in places where we might not have expected to get it if we thought that we could only do these other ways. So when I think of homology classes, I'm really just thinking of things like this, which I just call nested box cycles, that you can draw a bunch of nested boxes, and that gives you a torus. It turns out that for homology of points in the plane, this is pretty much all that you get. The homology really is just formed by these kinds of pictures. So to be a little bit more precise, there is a set of nested box cycles that forms a basis, a Z basis for homology of points in the plane. So it's a free abelian group, and every element of homology is uniquely a Z linear combination of this specified set of nested box cycles. So that's very nice for points in the plane or squares in the plane. And then for squares in a rectangle, it seems like it sort of should be like that there aren't things that are really a lot different from nested box cycles, but a lot of that is unknown. So here's a list of false and not necessarily false things that we might hope are true for bringing this situation with the whole plane into the situation where the squares are confined to a rectangle. So, okay, here's the first hope. We might hope that, like with the plane, the homology of the configuration space of squares in a p by q rectangle is also generated by nested box cycles. This is false. One sort of idea for why it's false is that homology of well, maybe I take that back. Maybe I can't say quickly a true reason why it's false, but it is false. However, one thing that I do want to be true is that nested box cycles might tell us for which degrees of homology do we get something that's non-zero. So suppose that we have some degree of homology, number of squares, and dimensions of rectangle where we cannot draw a nested box cycle because there's just no way to fit one. So if there's no nested box cycle with a given J, that's the degree of homology or the dimension of the torus, N, the number of pieces, P and Q, the dimensions of the rectangle, then what I would like to say is true is that there's no homology in that degree. I don't know if that's true. I hope it's true. Then I'll say is Hj of the configuration space equal to 0. So if we can't draw any homology at all, is it true that there's no homology? I don't know if that's true. Here's another hope that is just false if you hope it in the most naive way, that if you draw different nested box cycles, they should be linearly independent. This is sort of false for easy reasons, which is that for configuration space of points, there are relations that you can have between nested box cycles. So what you might actually want is something a little bit more refined than this, to say that, you know, if there's not sort of an easy reason why they should be linearly dependent, then they really are linearly independent. I don't know exactly what that formulation would be. But one thing specific that I can say I don't know the answer to is whether the homology for squares in a rectangle is free abelian like it is for squares in the whole plane. So just like some z to the k. It seems like it is. For squares in sort of a rectangle that's long enough, if you just have an infinitely long rectangle or one side length is n, then we do know that the homology is free abelian. But for a rectangle that sort of is smaller than n in both directions, we don't know, but it kind of seems true.
Hannah, can I ask a question?
Sure.
Somehow I've got myself confused. So let's start out with the fact on the bottom left. So a set of nested box cycles forms a z basis, and this is in the unbounded plane, right? So by z basis, you mean it's a z generating set and also some independence properties, or?
Right. So that the J homology of the configuration space of n points in the plane is z to the k for some k.
Yep.
And so those, you can pick those k generators to be cycles in homology that do look like something like this.
Okay. And then hope 3 and 4, in 3 you say they're not linearly independent. Oh, I see. And in
well,
hope
you just
4,
have to choose some subset of them.
I see. You still get, hope 4 is open. You hope you get z to the k, but k is going to be smaller than you might, than hope 3 would have suggested. I get you.
Or yes, so something like that. Yeah.
Okay. Thanks so much.
Okay, so to talk about homology, it turns out we also want to end up talking about cohomology at the same time. It's not really a separate question because it's always helpful for us to be able to pair cohomology classes with homology classes. So if you want to prove something about homology classes, you might want to use cohomology. For instance, if you have a homology class constructed using a torus, one of these nested box cycles, or something else, and we want to show that it's non-zero, then one simple way to show that it's non-zero is to exhibit a cohomology class that pairs with it and gives something non-zero. Similarly, you can show that homology classes are distinct. You could show that they're linearly independent. And if you have a homology class that you think doesn't actually fit in a P by Q rectangle, cohomology could help you show that too. So to say that a little bit more precisely, in this example with our 5 squares going around each other, suppose you wanted to show that that doesn't fit in a rectangle where one of the side lengths is smaller than 5, like 4. What we would actually be asking is there a homology class with width 4 that when we include it into the homology class where you have enough room, you have width 5, then it's homologous to this one. Is that possible? And then the answer you could show is no, using cohomology. So here's how I think of cohomology. What I do is I take pairs of boxes and I keep track of the vectors between them. So here I'm going to draw a vector from box 1 to box 2. That's going to be a non-zero vector. So I can normalize it to unit length and I get something in a unit circle. I could also keep drawing more arrows, like I could keep track of the vector from box 2 to box 3 at the same time. Keeping track of both of those gives me a map from configurations to a 2-dimensional torus. So that's what I have down here. If I draw J arrows, first of all, there's this inclusion. I don't really care how big the rectangle is to define this map. The map is still defined regardless of the size of the rectangle. I have this map to a J-dimensional torus if I draw J arrows. So let me just keep drawing some arrows here as an example. I can kind of draw the arrows wherever I want, although it turns out that if I draw any cycle of arrows, the sort of they won't happen independently, and so what I get will not it'll be 0 in cohomology. So I don't want to draw any cycles. That's why I say directed forest at the top. So here's my map. I'm going to call it G. Let's call it G. So I'm keeping track of the vector from 1 to 2, from 2 to 3, from 2 to 6, from 3 to 4, and from 3 to 5. So I have a map to a 5-dimensional torus. And if I want to evaluate it on this configuration, I get some tuple of directions, like this one, this one, this one, this one, and that one. And this sort of tuple is the element of my 5-dimensional torus that this configuration would map to. And why is that a cohomology class? Because my torus has a fundamental cohomology class and I can pull it back to the configuration space. So that's how I think of producing cohomology classes for configuration spaces of squares. Okay, so here's where I can get to some ideas about the theorem that we proved. To show what kind of thing that we proved, I want to say it a little bit more concretely by talking about one special case that's easiest to visualize. So I already said how you can have two squares going around each other in a 2x2 square. Suppose that I just do that over and over again next to each other. I have a big rectangle and it's completely tiled by 2x2 squares, each of which has two squares going around in it. The question, is it allowed to be repeated labels? The labels are distinct. Right, the squares are labeled 1 through n. There's also, you could ask all the same questions about homology and cohomology if the squares are unlabeled. And I guess you could also ask them if some of them are interchangeable and some of them are not interchangeable. For the kinds of things that we've been thinking about, it's normally easier to consider all distinct labels and then sort of later think about the action of the symmetric group permuting the labels. And the sort of geometric and topological behavior seems to be about the same either way. So we prefer to use the easier version. So I have a big rectangle and I'm imagining that I can have two squares going around each other in each 2x2 rectangle, 2x2 sub-square. So one conjecture that I have, I like to say just because I think it's easy to have intuition about. Suppose that I am thinking of degree of homology greater than PQ over 4, which is the number of 2x2 squares. Then what we don't know how to prove, but I feel really should be true, is that there's no jth homology. So regardless of n, equals 0, regardless of n. And this is because if you try to draw a nested box cycle, it's going to be impossible for such a large J compared to the area. Like if you wanted to draw a nested box cycle from scratch and try to get as much degree as possible compared to the area, you would end up doing this, tiling a big rectangle by these 2x2s, because having any nesting uses up somehow too much area for the amount of J that you gain. So it really seems like you shouldn't be able to have homology if the J is too big like this. But we actually don't know how to prove this. What we do know how to prove is that if you replace PQ over 4 by PQ over 3, then it's true. But I would like to know it for PQ over 4. That really seems true. So, and then another, so, okay, we often ask two sort of, well, so you on the one hand can ask whether homology is 0. And then on the other hand, you can ask if it's not 0, can you take like a sequence of values of the size of the rectangle, the number of pieces, the degree of homology, and ask for the asymptotics of the Betti number, the dimension of homology. And so here we can ask what happens for this picture of tiling a big rectangle with these 2x2s. So that's the scenario I list here. P and Q are even. Our rectangle is even number by even number. J is the number of 2x2 boxes that we've tiled with. And N is 2 times J. We have 2 pieces in each little box. Then we want to estimate the dimension of homology. And the theorem, so I attribute this to Bob MacPherson. This is sort of the beginning idea of our paper together. The dimension of homology, we estimate, is at least n factorial over 2 to the j. So what does this number n factorial over 2 to the j represent? Well, we can make one cycle that has these j pairs going around. That's one non-zero element of this homology. And then you can look at what happens if you take that one cycle and then you permute the labels. So this number n factorial over 2 to the j is a count of permutations. So you can look at all permutations, but then if you swap the labels of the 2 pieces in one 2x2 box, you get the same homology class. That's just like rotating the circle by half a turn. So you exclude those and you say that within each box, the 2 pieces have to be in order. This is the number of cycles that you get. And then the argument is that they turn out to be linearly independent. So we make our cycle with j pairs, we permute labels, keeping each pair in order. And then these cycles are linearly independent. So I want to contrast this with what would happen if instead of that rectangle, you have all of the space in the plane. Then each pair would be able to move to wherever, and you would be able to move them so that as long as the same pieces are paired, if you move those pairs to different places on your rectangle, you would get the same homology class. In this case, all of the ways to permute the pairs as pairs are different homology classes and linearly independent. So that's a much larger size of the homology group in this case where we're in the rectangle. So our theorem is a generalization of this estimate, this lower bound on dimension of homology for the picture with the sort of the checkerboard rectangle. It's an asymptotic result. We're looking at dimension where you have these 4 different parameters: the degree of homology, number of pieces, and the dimensions of the rectangle. And you want to know what happens when they're all going to infinity. So the way to get like one sequence of these situations, so we have only like one parameter to worry about, is to package them so that the degree of homology, the number of pieces, and the area, P times Q, are all growing together in approximately constant ratio, similar to this case with the checkerboard. So I'm going to have N over PQ, whoops, N over P times Q, and J over P times Q, each approaching some constant limit. And I want the parameters all to go into infinity. So I'm going to say, without loss of generality, P is less than or equal to Q, and P is going to infinity. So P is going to infinity, so Q is going to infinity. The areas are going to infinity, and that means these numerators N and J have to go to infinity in order for the ratio to approach a constant. So this is the situation I'm thinking of. I guess here on the left, what we have is N over PQ is 1/2. J over PQ is 1/4. Okay, so here's the theorem. So, well, interior of the feasible region. I haven't said what this is, but what it means is that in some earlier work, we found some possible x, y that are these ratios, N over PQ, J over PQ, where we know homology can be non-zero. There are some other situations where we're not sure if it's non-zero. In that case, we don't know how to estimate asymptotically how big it is because we don't even know if it's non-zero. But for this region where we know it can be non-zero, then we do have this lower bound on how it grows. Well, lower and matching lower and upper bounds. So I say grows like n factorial, whereas if instead of the rectangle you had the whole plane, the dimension of homology would only grow like j factorial, where j is sort of a constant factor smaller than n. And grows like here is maybe not what you would usually assume. I don't mean that it's within a constant factor of n factorial. It's something weaker than that. What I mean is that if I take the log and then I divide by the log of n factorial, then the limit is 1. Log of n factorial is like n log n. That ratio does go to 1. And so in some sense, we're saying that the biggest growth is like n factorial. But for instance, not just multiplying by like a polynomial factor would count as the same, but actually multiplying by an exponential factor, a constant to the nth power, preserves this sort of factorial growth rate. So it's sort of a sort of not a very fine estimate, but it does show that similar to this checkerboard special case, we get a lot more homology, or a lot more homology classes that are different even though they would be the same if we had the whole plane to work with. So that's our new theorem. And I guess I'll stop and stop for questions. Thank you, everybody.
Thanks so much, Hannah. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. Questions for Hannah? Let me start with one. Have you thought at all about like the 3D version of this problem?
So it's a reasonable thing to think about, especially with the molecules interpretation. Molecules make more sense in 3 dimensions than in 2. I mean, as an application, not necessarily that the math is easier or harder. I think for what we are doing, the 3-dimensional version of all of this is very similar. So similarly, if you look at the configuration space of n points in R3, it's really a lot like points in R2, except the circle parameter for when you have each arrow is replaced by a 2-sphere. But everything really just goes up a dimension. And I think the other things that we have, if you just tried to say them in 3 dimensions, generally it would be pretty much the same. So I think that's a good reason to work with 2 dimensions where it's easier to say and draw things. We haven't noticed things being really different in more dimensions.
Other questions?
Could you quickly go back to your cohomology class construction? So here you're including your CNPQ into CN just by forgetting the box.
Yeah.
And then you're looking at this map to the torus. Does this then mean that these are really, I mean, it looks to me like you're only really getting cohomology classes on CN in this construction, and then you're sort of pulling the MAC to CNPQ. Does that actually tell you something?
Yeah, so I was sort of wondering whether this would seem like a weird loose end when I said it like this. So what happens is that you can think in this way and actually get more cohomology classes that are just on the smaller configuration space. So what you would do is you can think in sort of a dual way in terms of intersection number. If you have one of these maps to the torus, Tj, you can take one point in the torus that you're interested in and take its preimage to get some kind of submanifold consisting of configurations where, you know, specified pairs are at specified sort of angles to each other. And then you're imagining what the cohomology class is doing is if you have a homology class, it has some intersection number with that submanifold, and that's the way that you would pair them. And then that submanifold, if you look at its restriction to the smaller configuration space where you just have a rectangle, if it breaks into multiple connected components, then each one of those is its own cohomology class, and then they add up to equal the cohomology class that's on the larger configuration space. So that's one way that you can get more cohomology classes and talk about cohomology classes on the smaller configuration space that are different from those where we don't care about the rectangle.
Thank you, that's awesome.
Further questions?
So that does end up being a major part of the argument for this this new theorem is breaking up the cohomology classes in that way.
I have a question. Is it reasonable to try to do, say, small computational experiments to try to, compute some of these homology classes on a computer for small sizes? Could one try to compute some of these things on a computer, or is that hard to do? And if it is potentially doable, have you tried it?
So we have a paper that is, I don't know if it's actually published that you can see it on the publisher website, but yeah, a paper previous on this. So with Matt and Bob and Uli Bauer and Kahle Spentlove, a paper about sliding squares in a rectangle, where we prove some things about the configuration space is homotopy equivalent to a nice cubical complex. And then you can do computations on that nice cubical complex. So it was mainly Uli and Kahle who were doing computations. You can't get anything really big because with what we were doing, you sort of always get a factor of n factorial in counting how many cells that you get. So even if you try to do something really fancy to decrease the number of cells, it grows fast with n, which is the number of pieces. So you could get about up to like 6 pieces and say something about what is the homology when those 6 pieces are stuck in different dimensions of rectangles. That's about how far the computer experiments have gone. But yeah, that was helpful for starting to think about sort of these conjectures, like the naive homology hopes, this thing that, like, it doesn't seem like you get homology when there's no nested box cycle, which we wouldn't have been able to have really any support for without those computational experiments, because you, like, how do you tell, like, there's homology that you didn't realize how to draw? But it seems like not. And similarly, that there pictures like this we realized were important because there was more homology than we were able to draw just for pictures like this one. So that has been useful.
Yeah, I appreciated Rolando's question about labeled versus unlabeled. Could you do simulations with unlabeled cubes and maybe go further if this n factorial is less of a problem?
Right. That seems, now that you say it, that seems like a good thing to be doing. And I can't remember what the status is of where we left that off, because yeah, it would be, you would get some nice cubical complexes that are a lot smaller, and you could compute homology and some things. I think either we started doing it and then didn't take it very far, or just didn't start. I don't remember why. It may have been that we didn't have a lot of conjectures ready about what you would get. So we didn't know what we would compare the numbers that we got out to.
Yeah.
But that does seem like a good thing to continue to be doing. I had just forgotten about it, but that was, sort of an obvious next step.
Cool. More questions? Well, if not, thanks so much, Hannah, for a fantastic talk, and thanks everybody for the nice questions, and let's end the recording here.